We're going to continue using the derivative table and build our integral table from it by taking the reverse order of the derivative component. Now, we can directly take the integral of each of the x and each of the negative x, right? An exponential growth term and an exponential decay term. Before that, we're going to look at a case where we took the derivative of the natural log and see how we can get an integral of a function to equal the natural log. Now, we're not going to take the integral of the natural log just yet. We don't have all the tools to be able to do that. But we're going to see the natural log come out as a result of an integral. Remember, the natural number e is about 2.7, and the usefulness of it is how the derivative of each of x was equal to each of x, and the derivative of each of negative x was equal to negative each of negative x. So these important properties will come out again when we look at the integral. But first, we'll look at the integral of the polynomial x to the power n. We looked at that a couple of videos ago, but we'll use that as a starting point to look at the natural log term. From the derivative tables, we know that the derivative of x to the n is equal to n times x to the n minus 1. And from that, we were able to get this relationship that the integral of x to the m was equal to 1 over n plus 1 times x to the n plus 1. In this case, the indefinite integral, we have to add an extra constant. But there is a unique case when this doesn't work. And so I just want to show quickly where this case comes from. Right? We showed in a previous video that integral of x cubed will give us 1/4 x to the 4th. Integral of x squared give us 1/3 x cubed. Integral of x, this is a m value of equal to 1, will give us 1/2 x squared. Integral of a constant, this is basically an x value of 0, right? X to the 0 give us 1. This will give us a constant times x plus a constant, right? Just applying this equation there. We know that if we have 1 over x cubed, this is basically saying m is equal to -3. We would get negative 1/2 x to the negative 2, or x to 1 over x squared. If we have 1 over x squared, this is basically saying m is equal to -2. In this case, we'll get -1 x to the negative 1, right? 1 over -2 plus 1 will give us -1 right there. And then x to the power -2 plus 1 will give us x to the negative 1, or 1 over x. We also recognize that this doesn't have to be an integer, right? So it could be something like square root of x, which is x to the power 1/2. We could do 1 over 1/2 plus 1 would give us 1.5, or 3/2. So 1 over 3/2 would give us 2/3 times x to the 1/2 plus 1, which is x to the power 1.5. That same thing as x times square root of x. It could also be 1 over square root of x. In this case, this would be x to the power -1/2. You plug in -1/2 right here, you get 1 over -1/2 plus 1. That would be 1 over 1/2, or 2, times x to the power -1/2 plus 1, or x to the 1/2, or square root of x. So all of this works, but there is one case that doesn't work. Hopefully you recognize which case it might be because of the title of this video. It is the 1 over x case. And why doesn't it work here? Well, in this case, m is equal to -1. And if I plug in -1 here to determine my coefficient, you get 1 divided by -1 plus 1, or 1 divided by 0, which is infinite or undefined, right? So you can't have that. Luckily, we've taken the derivative of natural log and found that that was equal to 1 over x. So that means that the integral of 1 over x, or x to the -1, must equal natural log. And here I show you a graph of natural log. Okay, so we can apply definite limits on it, right, to make it a definite integral. Right, so the definite integral of 1 over x with the limits, lower limit of 0, upper limit of 1, we basically do natural log, and we plug in upper limit minus natural log with the lower limit, 0. Remember what the natural log represents, right? It's e to the power of something is equal to the value in here, right? So what e is what? The natural number is about 2.7. So that number to what power will give us 1? Well, anything to a power of 0 would give us 1, right? So that's why that upper limit is 0. The lower limit says natural log of 0 is natural log of 0. The only way to get that is at negative infinity. And we can see this here, right, in this natural log graph, right, at x equals 0, we're at a vertical asymptote of negative infinity. We can also see this looking at the integral term, right, the area under the 1 over x graph. We see that we have a finite limit or height at the upper limit, and then we have an infinite term on the lower limit at 0, which is represented by infinity. So I can shift by 1, right? So I can go from 1 to 2 instead. And then so the integral itself is the same. The limits have changed. So now I'm at ln 2, which is about 0.7, and natural log 1, which is still at 0. I say that it's equal to natural log 2 here because natural law of logs, natural log 2 minus natural log 1 is the same as natural log 2 divided by 1. And if I shift it again, we can see that we're going to get smaller and smaller values, right? We start at infinity and we get smaller and smaller. It's reflected by the graph shown here. It's reflected by the values in the natural log, right? So if I shift to lower limit of 2 and upper limit of 3, we can see we get a smaller value. This is the same thing as saying natural log of 3 divided by 2 or natural log of 1.5. And I can keep shifting and you can see the effects in this graph here as it keeps getting closer and closer to the left side, or basically closer and closer to the value of 1, and this area getting shifting by segments of delta x equals 1 to the right. So the next thing we can take a look at is the exponential growth and exponential decay, e to the x and e to the negative x terms. So following the same logic as taking the derivative tables and reversing it to find the integral form, we can do the same thing. And I think this one's pretty obvious, right? The exponential e to x and e to the negative x. Take the integral of each and you just get the reverse, right? But this one's easy. It's a very interesting property of the natural number. The derivative of e to the x is equal to e to the x. So the integral of e to the x would also be equal to e to the x. The derivative of e to the negative x is negative e to the negative x. So the integral of e to the negative x would be negative e to the negative x, as we see here. So we can take a look at some limits. So for example, if I applied limits 0 to 1, I get e minus e to the power 0 for my lower limit, which is just equal to 1. And we see that reflected in the graph there too, right? I can choose different higher limits and larger range. It's the same exact idea. We just apply those limits to the e to the x function. I can also multiply by any constant, and looking at this rule and the integral rule, we can just pull the constant out of this integral and just solve for integral of e to x. So in this case, from 0 to 1, this will just be 5 times the integral that I found in the first step there. Right? So pretty straightforward, I hope. We can do the same thing with exponential decay, right? So this one's exponential growth because this is growing larger and larger, faster and faster. E to the negative x is exponential decay. It's getting smaller and smaller, faster and faster. So again, with 0, 1 limits, I basically have negative e to the negative x. So negative the quantity of the upper limit minus the lower limit. Upper limit being e to the negative 1, and which would basically be 1 over e. and then each of 0, which is 1, right? So I can swap them because of the negative sign in front. And then if I shift, right, I'm going to get a much smaller value in this decay behavior, right? So it's the opposite of my growth term. And then again, you just apply, plug in your calculator, your upper and lower limits into your function. And then again, if I have a constant multiplying term right there, you would see that the area here is just 5 times, or in this case, right, because constant is 5 times the original function integral from 0 to 1 as well. Right, so now we have, in the past couple of videos, right, we have for our polynomial term, the integral for that. We have for the trig functions, some of the trig functions, and now we have for exponential growth and exponential decay. And we start piecing these with more general rules like additive and subtractive and different kinds of substitutions. So we'll start building on those the same way we built on derivatives with additive and subtractive, product rule, chain rule. So we'll start building on there. Then we'll have all the tools we need for most of the integrals that you'll look at least at the basic level. Then we can take a look at some applications to apply the table of integrals and the rules of integrals to physical engineering problems that you might see.